Okay, on the next set of problems, I did copy the properties for you right here. Keep in mind how that works. Property number 1, log of any base of 1 is always 0. 2, if you have a log of an exponential, this is called composition, function composition. If the base of the log and the base of the exponential match, they undo each other. If you have an exponential function, a number raised to a power, if the base of the exponential and the power happen to be a log with the same base, they undo each other as well. You're left with just the argument, here just the power. So my goal is to make use of those. If I see one of those, that's very easy to do. I see one right here. I see the log base radical 7 of 1. That's automatically a 0, no questions asked. There it is. Now, if I take log base b of 1 equals 0, if I change this to exponential form, wouldn't you make this a power and this a power? Wouldn't you use the base to make use of that? Wouldn't these undo each other? And that's really what that's saying. Isn't b to the 0 1? Now, if I look at number 2, well, I'm trying to make use of, again, I'm going to call these properties by number. Property 2. So I want the base and the power to match. Isn't 10,000 10 to the 4th? That's 1 and 4 zeros. Now that those two match, by the second property, this is just a 4. The same deal, I see this is 11, this is 121. I will say that's the log base 11. 121 is 11 squared. And since those match, that's simply a 2. Now, sometimes those don't match. You could adjust the radical. We're not going to worry much about those since we're going to be using a calculator on the rest. Same deal here. I'm looking at this and thinking, okay, log base to 128. 128 is 2 times 64. This is 8 times 8. This is 2 times 2 times 2. And this is 2 times 2 times 1, 2, 3, 4, 5, 6, 7. Those undo each other and we left with a 7. And that's basically what this is. Here, I notice there's a problem that doesn't really match because that's not a power. Well, let me start first. Can I write this as 10 cubed? Now, what do you know about properties of exponentials? If I move this up, doesn't that become 10 to the negative 3? And now that those match, they undo each other, you're left with a negative 3. Same deal with 42. I'm glancing at this. At first glance, you might think, wait a minute, how am I going to make the argument 17? Well, start with, can you make that into exponential with the 17? Well, that's 17 squared. And if you move this up, properties of exponents, that's 17 to the negative 2. Those undo each other and you're left with a negative 2. So fairly simple, even though it's going to look like the homework is a lot, but it's really quick and simple. There's not much to do. Just make sure you practice this enough and get it out of the way before we get to the applications. And if I look at number 52, I notice that this is using property 3. I notice this is an exponential. The base is 0.4 and it happened to be the exponent is a log with the same base. They undo each other and you're left with a 10. A lot of teachers don't like this crossing that I'm doing, but it's all good. And here, do you see that the base of the log and the argument match? So you're left with a power. That's why I really don't emphasize that a lot, because it's a special case of this. What's the power of 1? And there it is. And on 56, I notice the base is a 2/3 and the power is a 2/3, that would be a negative. What if they don't match? Well, glad you asked. If they don't match, then we use something else. We use a change of base formula. But we're getting there. You guys always rush things. I'm gonna shrink this a bit. Okay. Now we have two special logs, and the reason they're special not because there's anything special about them, because of their base. That's what makes them special. And if you see a log, if I ever write a log, actually I did that a couple of times on this problem when I was writing this. Did you notice I didn't write a log, a base? If I write a log, just a log of x, then you are to assume that the base is 10. And if you have a log with a base of e, the same e, (718) ... then you could use natural log, ln. It has a lot of applications, and that's why it's in there. Your calculator can read a log base 10 and a log base e as well. It's programmed that way. Alright? So, if I continue on, still the same deal as we were doing up there. If you want to write this as a log base e, every time you see it, you could. Do you see that those match? That's just a 6. Isn't the base for this log a 10? Those match. I'm left with the power, which is a pi. Here, log base, that's a 10, of course. You don't have to write it. And that's a 10, of course. Log base 10 of 1 is a 0. And wouldn't these two end each other? And you're left with a 2, and 0 plus 2 is a 2. And here, this is a log base e of e, so you're left with the power, excuse me, which is a 1. And here, this log has a base of e, they end each other, you're left with the argument, and you will get 1 plus 35, which is 36. So there it is. Okay, now, if I take y equal a to the x, I know that's an exponential function. The graph of that will look either be an exponential growth so either something like this, if the base is bigger than 1. And if the base is between 0 and 1, then it's going to be exponential decay. Again, our sketch. And that's the point still 0, 1. So, if I really want it, I could have said, well, if x equal 1, right, then if it's growth, if the base is bigger than 1, that's definitely bigger than 1, and if we go for -1, that's smaller than 1. Here it reverses 1 a fraction and -1 something bigger. Well, if I take this, and if I want to find the inverse, to find the inverse, I would switch x with y. I would say x equal a to the y. And if I say solve for y, if you have an exponential, don't you log both sides? Aren't we going to use log of both sides to get rid of the exponential? Same base, those under each other, and y equal log base a of x would be the inverse. What do we know about the inverse? We know few things. One, we know the graph is symmetric with respect to the line y equal x. If I draw the line y equal x, if I flip-flop this graph, it would look like this. If I take the point 0, 1, switch x with y, that becomes 1, 0. And the important aspect, if I take y equals 0, switch x with y, that becomes x equals 0. And now if I ignore the exponential altogether and just focus on the graph of the log, I notice that here, the domain for the log is 0 to infinity, and the range is all real numbers. So given y equal the log base a of x, the domain, whatever this x is, you would set it to be strictly bigger than 0, just like we do a square root. Square root we set it to be greater than or equal to 0. Here we want it to be strictly greater than 0. And if I go to this graph, here it's easier to look at this. And if the base is between 0 and 1, this graph will just reflect, and it would look something like this. So, an easier way, you really should look at this graph here. So this reflection kind of helps. The main points are, if the base is bigger than 1, the graph looks like this. If the base is between 0 and 1, you just flip that, so it looks like this. And instead of growing, it's decaying as well. The same point, 1, 0, the same asymptote that doesn't change, and domain and range are identical. And that's basically it. So when I get to problem number 58, sketch a graph. Well, again, if it says sketch a graph, I need to label points. If I look at this, I notice the base is between 0 and 1, so I know the graph is going to pass through the point 1, 0, and it's going to look something like this. And I would label the asymptote clearly, done deal. And if I take, now normally the domain kind of helps you out. If you take the domain, you say whatever that is bigger than 0, that tells you the graph is to the right. Here, it seems this graph is shifted. And if you're not sure about where the shift is, well, you could find the domain before you start. You could say the domain, whatever you take in the log of, the argument, must be bigger than 0. So that means x must be bigger than -5. That's the domain. So that means instead of 0, it's really 1, 2, 3, 4, 5, a vertical line, label that clearly. And instead of the point being at 1, 0, well, it is 1 unit away. This graph shifted 5 units to the left. 1, so this point instead of being 1, 0, 1, 2, 3, 4, 5, you label that clearly. The base is 2, so that's the traditional log. And the last part, could have asked you to graph, but they say find the domain. Let's find the domain. Whatever you take in the log of, ln is a log, whatever you take in the log of must be bigger than 0, can equal 0. Which means now Anytime you start the problem with an even index radical, anytime you start the problem with a fraction, and anytime you start the problem with a log, you have to check your answers. So negative 2x is bigger than negative 6. What happened when you divide by a negative? So you would say the domain would be x such that x is less than 3. You could write this in interval notation if you wish. You could say negative infinity to 3. I really don't mind either or. When I get to 84, it's the same type of problem. I'll take the argument, whatever you take in the log of, and set that to be strictly bigger than 0. Subtract 9 from both sides. And divide by a negative 5. Whatever you divide by a negative, you switch the sign. And the same deal on the last problem. 22x plus 19 must be bigger than 0. 22x is bigger than negative 19. And if you divide by 22, x would be bigger than negative 19 over 22. So here I'm going to write the domain in interval notation. I'm going to say negative infinity to 9/5. And here I'm going to write it in set builder notation. You could use either or, x such that x is bigger than negative 19 over 22. And the homework is right there.